Hi, people. This recording is for those of you who were not able to make our supplemental physics session on Thursday from 11 till 12. I'm going to run through, this is Unit 5, Open Response Question 1, and I'm going to run through this pretty quickly. I've decided to do it on this format on my notebook, mostly because I don't have to do too many equations, and I have the question right here in front of me, and it's really easy to work with and refer to the drawings and stuff. If I'm just writing equations on my iPad, it's going to get harder to import all the images and the questions, etc. So I'm just going to do it like this. It will only struggle a little bit when I have to write equations, but I'm getting better at that, so that won't be too bad either. All right, so this is Unit 5, Open Response, question number 1, and it's a classic situation where a block slides down a frictionless ramp. If you read all the, I'm not going to read this whole thing to you, but this block X is released from some height and it slides down the ramp, and then it impacts block Y. It says down here they stick together and they move off together at some new speed. Now it's frictionless and the blocks stick together. So if you want the details, just read this. In fact, please do read this to get the details, but you'll see that it just says what I said. Oh, and block X is more massive than block Y. Okay, so the first question here, the first thing we're tasked with is to state the physics principles, laws, or equations that students could use to graphically determine the relationship between the release height of the block and the speed at which the block system travels after the blocks collide together. Right? So there's a real key word here, that one. And so we've got to describe two things, right? The basic principles that describe how they could determine what, the relationship between the release height of the block, and then also equate that with the speed at which they travel together afterwards, right? So we're not going to do the equation yet. I think that's next, but let's say it out loud, right? So I don't know about you, but when I look at this, I say, okay, is this motion? Yes, it's definitely going to be a motion problem, but it's sliding down a ramp, a frictionless ramp, and the ramp has a curve to it, and it's going from one height to another. So I'm not going to go with kinematics here. Kinematics and dynamics would get really hard with all these vectors, and this would be really difficult. The vector here would change. That's too difficult. What are we going to employ here? Conservation of energy, right? It's released from rest. So up here it has potential energy, and just before it impacts block Y, all that potential energy has turned into kinetic energy. So I'm going to say something just like that right down here. I'm going to say, let's see, state the basic principle that students can use to graphically determine the relationship between the release height of the block. Okay, so block X starts with only potential, PE gravitational potential energy. Gravitational potential energy. Block X starts with only PE gravitation, and as it slides down the ramp, that PE grav turns into, I'm going to say it out loud, kinetic energy. Okay, that's a big principle, right? Block X starts with PE grav and slides on the ramp. That PE turns into gravitational kinetic energy. It says here, even students could use. It says state the basic principles, laws, or equations. We don't have to put the equations in, right? Block X starts with only PE grav. I think maybe I would do this. Or MGH. They're talking about H here. They're talking about H for height instead of Y for y-axis. Same thing. They're both right. And then maybe I do this here too. MV squared over 2. Let's just keep it in the format we're used to. 1/2 mv squared. 1/2 mv squared. That's the Ke, right? It turns into kinetic energy. 1/2 mv squared. No work is done by friction. No work is done by friction. So the quantity of mechanical energy will stay constant, and the I think I spelled constant wrong. I need a T in there, and the KE at the end of the slide will be equal to the initial PE, gravitation. Okay, that's for the first part. That's for this figure 1. Right? That's a conservation of energy problem. And I hope you recall, this is very important, I hope you recall that during sticky collisions, we cannot use energy, right? And sometimes even bouncy collisions can't unless we see keywords like perfectly elastic, things like that. But if it's certainly during a sticky collision, I cannot invoke energetics here. And I know that right now you are thinking about conservation of momentum, because momentum does describe the collision very well, right? So to analyze the speed after the collision, the students will need to invoke the conservation of momentum theorem. The momentum block X had just before the impact is shall we say constitutes or is the momentum block X had just before the impact is the total momentum in the system. The two-block system will have that quantity of momentum after the collision. Okay. You don't have to use these exact words. I'm just describing this. You can say it in your own words that we're going to use conservation of energy for the frictionless slide, right? PE turns into KE. Over here, we're going to recall that energy does not work for inelastic collisions. And so over here, we're going to have to, block X, just before it hits, has momentum. And then it hits Y. Y pushes on X as X pushes on Y to speed it up. Y pushes on X to slow it down. And the forces are equal and opposite. And, if the acceleration of Y and the deceleration of X takes place over whatever, I don't know, a tenth of a second, then the forces exerted on each last for the same amount of time. So the impulse, the F times T, is the same for each. The delta MV is the same for each. However much X's momentum goes down, Y's momentum goes up, and the system stays the same. So you want to show the readers here, so don't get worried like, oh, I can't quite say it in the words that he said it in or anything like that. Well, I've been practicing for a while. But what the readers are going to look for is that you recognize that this is conservation of energy, but you cannot use energy for collisions unless it specifically says elastic. Right? Even if they bounce off of each other, unless it says elastic, there's still deformation of material, etc., and heat loss. And so we're still good. Just about every collision, you need to use momentum, but for frictionless slides down ramps and things of that nature, you can use energy. And that's what they're looking for. They're looking for you to say, this is conservation of energy, and this is conservation of momentum. And all the rest are details. Okay, derive an equation. Well, I hope you see that, they're asking questions here. They're trying to set you up for success. They really are, right? They're trying to set you up for success. You're going to have an energy equation. And then you're going to write a momentum equation. And all you're going to write is energy before is energy after, and momentum before is momentum after. And then we're going to have to combine those two statements. So let's get that. This is going to be the part where I mess around a little bit with the keyboard. It's a little bit tricky to write equations in this format, but that's okay. I'll try to be quick about it. Derive an equation that relates to the release height so this is the tricky part, but you'll see what I mean here. I'll point it out as we go. So let's turn down that font again. So energy before equals energy after. Okay, that's for the slide. So this is for the first part. I'm going to derive two equations here. You'll see why. And energy. So I say, okay, well, what is it? Well, it was PE gravitation. PE grav got turned into and was equal to KE. Okay, that seems fair enough. If I can't remember what PE grav is, I can just look it up in my equation sheet. But I remember, and so do you, that it's MGH. And same thing with kinetic. If you can't remember, you just look it up. Oh, what's KE again? Oh, 1/2 mv squared, right? So there's an equation. I'm going to simplify it because, well, there's m's on each side and there's a pesky fraction. So I'm going to go ahead and say, 2 GH's equals v squared. And I'm going to take it one step farther, and I'm going to say that v equals root 2GH. And the way I'm going to do that is like this. This is meant to be a radical. Sorry about that. That's not the best radical I've drawn. It's not the worst either, but try to do slightly better. There's a very important equation right here that v is root 2GH. Right? V is root 2GH. We're going to want to put that in our pocket and use it in a few minutes. Okay. Okay. Let's see here. Oh, you know what? I'm so sorry. We don't even have to do that. I took it. We're going to want the h here. We're going to want this in terms of h. So let me just go back to here. Sorry about that, guys. We're going to want that in terms of h. So boom, boom. Oops, wrong guy here. Yeah. So let's just solve this for h. Right? Let's just divide by each side by 2g. So h equals v squared over 2g. H equals v squared over 2g. That's the one I want to put in my pocket. That's the one because we're writing an equation for height, right? In terms of release height, we're going to relate velocity to height. Okay. Well, there's an energy statement. There's an energy statement, and over here, figure 2. We're going to do something similar, except it's a momentum statement. All right, so here we're going to say, oh, the momentum before the collision. This is for figure 2. This is for figure 2, right here, the collision. The first equation I wrote was just what's going to happen to this block as it slides down the ramp. Its PE turns into KE, and I've got options how I can express that, as you just saw. And then I'm going to write another equation here, and it's not energetic. Again, it's momentum for the collision. So let's write that equation for the collision. Momentum before is, wait a second here, momentum before is the same as momentum after. Okay. Well, the mass of block X, let's just go like this. Wait. So MV of block X before the collision plus the MV of block Y before the collision is equal to the MV of block X after the collision plus the MV of block Y after the collision. Now, we can clean this up a little bit before we take any more steps. I hope you recognize that the block Y has no momentum before the collision. It says it down here, it's sitting still. Right? Block Y is stationary. So block Y has no momentum before the collision. Block Y has no momentum before the collision. That's 0. And the other thing I want you to recognize is that these things stick together. These things stick together. So whatever their velocities are, they're the same as each other. Right? So velocity of block X after the collision is the same as velocity of block Y after the collision because they're stuck together. It's the same velocity. So these subscripts here after the collision need not be there because the V's are the Vx prime and Vy prime are the same value, right? The same value, right? So now I'm just going to write this mv on the x-axis, just cleaning it up a bit, mv on the x-axis is equal to mv prime plus mv prime. Now let me subscript the m's, because that's the mass of block X here, and this is the mass of block Y here, right? So the m's are not the same, but the velocities are. So what can we do? Well, we can factor out that v. So mv before the collision, right, is equal to v prime times mx, oops, wrong button there, mx plus m sub y. Okay, so I think we're getting somewhere here. Yeah. Let's do this. So let's go ahead, and so we want to write an equation that relates height of the initial release height to velocity after the collision. Here's the velocity after the collision, and I don't have anything about height in here. Maybe actually, you know what? I think I was right when I thought I wasn't. This equation is okay. I got to get that radical back in there, right? That equation. I mean, of course it was okay, but I just wasn't sure that we needed it. But actually, it turns out we do. Because the velocity of the block X just before it hits block Y is root 2gh, right? So the velocity of block X right here, that's the mv of X before the collision. That v right there is before the collision. That's the momentum the block had right here when mx was sliding but had not hit Y yet. It had velocity. How much velocity? Root 2gh. So that v right there is root 2gh. I go back here and I do this, and I say, okay, well, m times vx before the collision. Well, vx before the collision is root 2gh, right? I'm going to put the radical in there in a second. Equals this. Okay, and that's a root 2gh, right? That's a root 2gh. So let me get that in there. Thickness, and I don't know what color I'm at here. Boom. Root 2gh. Try to get a radical in there. That didn't work. Okay, whatever, doesn't matter. Root 2gh. So m times root 2gh, and that's the m of x. M times root 2gh, and that's the mass of block X right there. Flapping here, hold on. There it is. M sub x. That's the mass of block X, of course, before the collision, right? Times root 2gh is m, so there's m times v is equal to v prime mx plus m sub y. And all I have to do is solve this for v prime by dividing by the total mass, right? So my final equation right here is going to be, simply, well, maybe not so simply, but my final equation is v prime equals m sub x times root 2gh. Again, I'm going to put the radical in a second. And that's over the quantity, right? I'm solving for v prime, so it's that divided by the total mass, divided by this. It's probably slightly faster to copy and paste it, right? And then this gets the radical. This gets the radical right there. There's my equation. Okay. So I'd like to point out again and really, really try to impress upon you that they really are setting you up for success, because what they're asking you to talk about here and recognize energy and momentum here and here and talk about it here, now they're asking you to write that same equation, right? And so if you're talking about energy in the first instance and momentum in the second instance, well, that's a really strong hint. You're going to write two equations. Now, um, all these formulas are accurate. Everything here is right, but they're looking for this one. And the reason I know they're looking for that one is because they say right here, it relates the release height and the speed of the two-block system after the collision in terms of m's and fundamental constants. So we need h's, v's, and m's, and that's it. And fundamental constants such as g, right? So m's, v's, and h's, and g, and that's what we have here. If you, you know, if you just write the energy equation, like let's say you stop here on the energy equation, right, which is fine. And then you write the momentum equation, and maybe you just don't see that substitution. Maybe you only get to here. Maybe you only get to there. Maybe you only write that. Or how about this? Let's back up even farther. Let's back up even farther. What if you really just, okay, I know the energy is being transformed. I know it's PE grav into KE, and I know that. And what if you stop there? And then same thing with momentum. Oh, I know there's momentum, and I know that the one, that's zero. And so, boom. And what if I stop here, or maybe even at the next one? You're still going to get the vast majority of credit because you are recognizing we've got energy here, but we can't use it here. Now, this final step is going to be the final full credit move. But you would get, if this were a 10-point problem, this part of it would probably be about a 5-point issue. But if this is worth 5 points, let's say, if you do what I've just put in these yellow boxes here, you're going to get 3 or 4 of them. So never throw your hands up in the air. Never give up, and never say, "Oh, there's no way I'm going to complete this and get it only in terms of these values up here." Maybe you will, maybe you won't get this, but think partial credit and think lots of partial credit, because what the readers are looking for is for you to recognize that energy can be used to analyze the frictionless slide, but energy cannot be analyzed to use the inelastic collision. And so, if you just had PE grav equals KE and MV equals MVX plus MVY after the collision, if you just had that, you're still going to get a solid 2 or 3 points out of 5. And then if you take it a step farther and you recognize the velocities are the same after the collision, and you get to here, we're talking 4 points out of a possible 5. And then to make the final substitution would get you the full credit. But again, they're setting you up for success. They're asking you to write about it. And if you recognize it, you're going to have 2 equations. And if you find yourself in that situation where they've asked you to write about it, you find yourself, oh, okay, I'm going to use energy and momentum. I'm going to write 2 different equations. Well, they're probably going to want you to combine those 2 equations to satisfy the constraints that they're placing upon the formula they want to see. Okay, so we get to this formula. How fast are the blocks sliding after the collision? Well, it's the mass of block X times root 2gh divided by the total mass of the system. Okay, so there we go. Now to the next page, the next part of the question is this. Design a procedure that you could use to graphically represent the relationship between the thing we just explored. And in the table below, list what you're going to measure, the symbol, and the equipment. Well, you know what you're going to do? We just came up with an equation. So those are the things you have to measure. And so what are you going to measure? Well, you're going to measure the velocity after the event. You're going to measure the mass of block X. You're going to measure how high you put block X. And you're going to measure the mass of block Y too. So you're going to measure velocity, masses, and height. And that's it. So how do you measure? Well, quantity to be measured. Let's get it done. All right, quantity to be measured is, well, we need the mass. Mass of X and Y. Right? Okay, well, symbol, M, and equipment. You could say scale. You could say balance. anything reasonable, right? And what else do we say we're going to measure? Oh, we're going to measure the height. Where we drop it from. Okay. Well, the symbol for the quantity. How about h? And what are you going to use to measure height? Well, how about a meter stick or even a ruler? If you wrote ruler, that'd be fine too. And then I think we said, we have to measure velocity. So after the situation, we're gonna calculate. If I release it from 13 centimeters high, how fast will it be going? You're gonna have a idealized. You're gonna have a theoretical number. And how are we gonna see if it's actually the real number? Well, you could. Oops, sorry about that. So how are we going to measure velocity? Symbol for quantity, v. How are we going to measure it? Well, you could say simply, I would suggest just say this. We didn't use it really until the end of the year, but I would just say motion sensor. Because then when you describe your experiment, you can just say use the motion sensor. But if you don't remember that and you want to do it old school, you could say meter stick, timer, tape, some such, and you can just do velocity equals displacement per time, right? Either way is fine. This is sort of a shortcut, and it's totally acceptable. It is totally acceptable because motion sensors are found in virtually every physics lab from high school upward. Okay, so describe the procedure to be used, referring to the table, provide enough details so another student could replicate it. Okay, well, so we just have to, again, I really want to impress upon you to keep it simple, right? So measure the masses of block X and block Y. Okay, measure the masses of block X and block Y. Place block X at a known height on the ramp. Place block X at a known height of the ramp. Release the block and use the motion sensor to determine the speed of the system after the collision. We did something really similar to this. I mean, we didn't put it on a ramp, but we used a spring to propel one of the carts at our momentum lab, station number 4, I do believe. Yeah, station 4. You did something just like this, but you weren't using a ramp, right? You weren't using a ramp, but we had a sticky collision, and the initial velocity wasn't caused by a ramp. It was caused by, what was it? It was a spring. The spring piston pushed the cart into the other cart, and they collided. And we graphed. We used the motion sensor, and we saw the velocity of the car, and then it hit the other one, and it dropped to some other value, right? So that's what's happening here. That's exactly what's happening here, right? So measure the masses of block X and block Y. Place block X at a known height on the ramp. Release the block and use the motion sensor to determine the speed of the system after the collision. Now, that's pretty much all you need. But it does say provide enough detail. Oh, no. It says include steps necessary to reduce experimental uncertainty. So would you just do it once and say I was right or I was wrong? No, you certainly would not. And would you just do it from one height and do it one time? No, you would do it from multiple heights, multiple times. So perform experiment. Just pick a number and make it make it 5-ish. Perform experiment 5 times from various heights to determine if the general formula is applicable, is accurate, is correct, any of the above, right? But whenever they say include steps necessary to reduce uncertainty, that's where you say perform experiment 5 times and change like the height variable and see if you always predict velocity, right? So I would do it. What's the velocity going to be if it's at 12 centimeters? What's the velocity going to be if it's at 22 centimeters? What's the velocity going to be if it goes from 6 centimeters? And you should get accurate results each time. And if your results are within 5% or so of your predicted value, then you were successful, right? So the key to reducing uncertainty is multiple trials. So you're going to see that. They're going to say how you're going to do it, and you're going to say multiple trials. Okay, students repeat the experiment, but replace X and Y with blocks W and block Z. Okay, as shown in the figure. They have identical masses, and when the experiment is conducted, they observe the blocks do not stick together. That says they don't stick together. It does not say elastic collision, okay? It does not say that. You know that often things don't stick together, but it's still inelastic. And I would just like to reference a really simple example. When you drop a tennis ball from the height of your forehead to the floor, it does not bounce back up to the same height. It probably comes up to your waist or something, right? Why? It's not a sticky collision, but it's still inelastic, right? Energy was lost because the tennis ball bent and there was a deformation of material. And when you deform materials, there's heating involved, and heat will rob you of energy, and the potential energy won't be the same. Right? So that's what's going on here. When the experiment is conducted, the students observe the blocks do not stick together, as shown above. The students predict the speed of block Z after the collision by assuming the collision is perfectly elastic. Well, you know what they say about assuming, okay? But by assuming the collision is perfectly elastic, they then collect data about the actual speeds of both blocks immediately after the collision, as shown in the table. Okay, so let's take a quick look at the table. Their predicted speed after the collision for the second block, the predicted speed is about 1.6, but the actual speed was 1.3. Not going quite as fast as they expected. About 2. Oh, but it was only going 1.6. Yeah, about 2.4. Oh, it was only going 2.1 though, and I predict it's going to go 2.7, but found it's going 2.5. So, well, what's going on here? Well, in each and every case, they're not going as fast as the kids thought. Why? Because the collision was not elastic. Energy was lost during the collision due to bending of materials and deformation of materials. Okay, so they're going to ask us about that here. Why does the speed of block Z after the collision not agree with the actual speed? So I've just said it to you, but let's write it down. Even though the blocks did not stick together, the collision was inelastic. It was inelastic. During inelastic collisions, mechanical energy is transformed into thermal energy. Oh, you can just write heat. Mechanical energy is transformed into heat. Heat energy. Right? During inelastic, mechanical energy is transformed into heat energy due to deformation, deform the materials, deformation of materials, due to deformation of material. This energy loss results in less mechanical energy in the system, and therefore a lower kinetic energy than expected. The the block? I almost said cars. The blocks are not traveling as fast as expected due to this energy loss. That's it, right? And again, if you're thinking to yourself, oh my gosh, I don't know if I would have said it like that, you don't have to say it just like this. You just have to recognize that it's not elastic, right? There's keywords here. The students assumed it's elastic. Well, you need to recognize it's not elastic. If it was elastic, all the energy would be conserved, and the reality would be much closer to the theory. But this is clearly an inelastic collision. So the takeaway here is they're looking for you to recognize that that things can bounce off of each other and still be inelastic. Okay, things can bounce off of each other and still be inelastic. Elastic collisions, truly elastic collisions, are very, very rare. They happen at the subatomic scale. They happen with fields, like magnetic fields pushing on magnetic fields, or things of that nature. When fields deform, energy doesn't really get lost. And curiously enough, they occur pretty well with things like billiard balls, because when billiard balls, pool balls collide, there's virtually no deformation of materials, right? Billiard balls don't bend at all when they hit each other. And so very little energy gets lost. Even though some does go away as sound, you can hear that distinctive click as the pool balls hit. But still, very energy is lost because there's no deformation of material. That's the key right there. They want you to recognize that collision is one in which things do not stick together, but nonetheless, it is inelastic. Okay, that's the end of this quick little video. I do believe, yep, that's the end here. And so I'm going to stop the recording and go on to Unit 5, Open Response Question 2 in a different video.